Hey y'all, I'm going to quickly go through lesson 3 notes. I'm not writing them because I wanted to give you time to copy and think about what I'm saying. My advice to you is this: I would watch the video, and then at the end of the video I will post each of the 4 worksheets one at a time that you can pause the video and copy everything down. So think about what I'm saying. Really try to stay in touch with the different processes that I'm explaining. And if you have questions, you're welcome still to put questions on the homework helper. The first 4 examples are actually covered in the I do, you do worksheets. So I'm going to leave this up for a couple seconds. Again, pause the video and add them to your notes. Starting with example 1, we're just simplifying. Notice how I added the E, which was not there as the base in this problem. So this is base E. The question that you're being asked is, what is the exponent of E that gives you E to the A? So there's like a little blank there that's understood. This thought process is what you need to be able to generate when you see a simplify problem like this. The answer that goes in the box would be A. In example 2, you need to recognize, well, if I have to simplify this, I need to be able to change forms. When you're adding the powers, which you are here, you have to remember that the exponent rule was that you were multiplying 2 bases. When I rewrite the problem with 2 bases that are the same, I then can use the rules in 1 through 7 to simplify. E to the 7th is simply E to the 7th, and E to the ln is A. Multiply them together. Example 3 is where we can use the opposite operations of transforming a logarithmic equation into an exponential and then solving. If you take a look in this example, when I go to solve in this problem, e to the 3t plus 5 base raised to the entire power is equal to y. My goal was simply to solve for y. We don't know what t is, so we don't have to worry about that. In example 4, we're asked to solve for k. K is located in the exponent of base e. In order to solve to get k out of the exponent, we have to take either the log or natural log of both sides. I chose ln because I was dealing with base e. I then can use the power rule to take the 2k, bring it out front, which I have right here. Ln e is the same thing as 1. 2k times 1 is just 2k. And then from there, I'm going to divide both sides by 2. Please take note on the right-hand side, that does not mean you can simplify by doing 10 divided by 2. Ln of 10 is a decimal, which then you divide by 2. The approximation of the solution is 1.51. For our next problem, you can use your golden ticket and add these rules if you haven't already. When you're asked to take the derivative of e to the u, okay, u is symbolic for any exponent that would be up top. There are 2 parts to this derivative. The first is to write back exactly what you started with, e to the u, but then you have to multiply it by u prime, which is the derivative of whatever's in the exponent. So if you take a look at the next example we have here, e is raised to sine x. Sine x is our u. Notice the little squiggly underneath is the same thing back that you started with. Then you're going to multiply by the derivative of sine of x. Check out your orange sheet. That answer is cosine x. When I move to example 6, this one's a little bit more complicated. Okay? In example 6, first we need to recognize that we're asked to take the derivative involving a product rule. X squared times e to the x. which means I'm going to set this up to look like the product rule. Okay, this is just my x squared, this is my e to the x, and then I have to fill in these two spots. You're going to say, well, what are these two spots? Well, notice this first spot is the derivative of e to the x. That's going to take me back to this rule, so notice my big circle involves two parts. My derivative of e to the x involves two parts also, the squiggly part and the line. From there, I need to take the derivative of x squared, which is 2x. I then can multiply and simplify. The tricky part was number 1, identifying product rule, and then number 2, making sure that we use the new definition that we just learned about e to the u. Now, for my next problem down here on the bottom, I'm going to let you see all the work. This is an example of the quotient rule. Okay, so notice as I move down into this first line, I set up my structure for quotient. Structure, structure, structure. Something times something minus something times something over something squared. I filled in x squared, I filled in the x, I filled in the e tangent x. Okay. Now, when I'm asked to take the derivative of e tangent x, notice the purple circle. I had to recognize that as the e to the u definition I gave you at the top of the page, which means I need to have the original e to the u times the derivative of tangent x in this case. Over here, my 1 comes from what is the derivative of x. Okay. Then we've got some algebra to work out here. 1, 2, 3. This block is one term. One term. Minus multiplying these two things together gives me one term here also. So x times this times this. Now, notice here I have an x squared in the bottom. I can't cancel this x because I'm not taking an x from this term. So all this stays in play. I am simply going to take this 1, 2, 3 part single term, and I'm going to factor out e to the tangent x. Because notice I can take e to the tangent x out of this second singular term, all of which is over x squared. Now, my next problem is a really hard one. It looks simple enough, e to the xy, but that xy in the exponent is what's going to make this tricky. So here's what I mean by that. Okay. If I follow my purple circle at the top, it says that I need to take e to the u times u prime. The issue in this problem is that my u prime, as you can see here, has to be a product rule. I'm multiplying x times y, which means I'm going to have to use the product rule, and I'm going to have to use implicit differentiation. If you forget implicit differentiation, it was back in lesson 1, where if we have y's on the right side, we have to attach dy dx's to them, and then resolve to isolate dy dx. So take a look at my work here. There's that e to the xy. There's my derivative, which happens to be a product rule. Okay. So all of this that's in here is the derivative of x times y. First times the derivative of the second plus the second times the derivative of the first. Okay. Now we're about to get a little trickier. Notice when I analyze that, this gives me 3 total terms when I distribute the e to the xy. Don't I get the dy dx on the left, the first green box, then the equal sign, second term involving a dy dx, and then a third term that doesn't have a dy dx with it. According to implicit differentiation, I'm going to put my dy dx terms on the same side. I'm regrouping. Then from there, I'm going to GCF out the dy dx term, and I divide both sides by the quantity that's left after I take my GCF out. That leaves me with that final answer. This is a pretty hard problem, but you may see one or two of these on the worksheets. All right, next type of problem. New derivative definition. What happens if I have ln x? Okay, ln x has a new definition. It has two parts to it. You're going to take 1 over u, it should say ln u, and you're going to multiply it by u prime. So I tried to make this like a little bit of a star so you could see where my little caret was versus my little star in the problems. So if you look over here to the left, my u value is x squared minus 1. So 1 over u is here, times u prime is the derivative of u, which is 2x. Then I use algebra to simplify. What I have in the blue box is what I have here. Now, moving over to the next problem. U is going to be a quantity, cosecant x minus cotangent x. You cannot distribute natural log. So notice what I did first. Here's my caret, 1 over my u value, times the derivative of each one of these terms, the derivative of cosecant x and cotangent x I have here. This minus sign is the same as this minus sign. It's the same as this minus sign. So what you're seeing is this is the derivative of cosecant. This is the derivative of cotangent. The two negatives become a positive. Now at this point, some of you may stop and think that you're done. However, we can actually GCF and take out a cosecant x in the numerator, which allows us to cancel the quantities. All right, so in this next section, it's a review of power rule. Okay, so one of the things you're going to have to distinguish is, do you have e to a power? Do you have x to a power? Do you have, in notice example 12, do you have x raised to the x power? Each one of these have different strategies for solving. We'll talk more about this on the next lesson when we do a secondary worksheet. If I take a look, you can quickly copy these down. It should be simple power rule from when you were first taught derivatives. The trickiest one probably is this in yellow, x to the pi. Notice the pi comes out front, pi, and then the rule says take whatever the exponent is and subtract 1. You can leave it in variable form. Now, example 12. Okay. Example 12, we have the rules listed on the right-hand side. We also are going to refer back to our ln of u derivative. So, I'll post this for you to see. Anytime you have x to the x power, this is when the exponent is a variable. Okay? The rules say take the ln of both sides. So notice I took ln of both sides. I then brought my x out front, which is going to be my power product rule. Power rule. Okay? This is where we get tricky with our calculus. On the left, do you notice that I used the rule over here, ln of u? Here's my caret, and then here's my star. the derivative of y is going to be dy dx is equal to, then I have a product rule. X is here, ln x is here, then I have to take the derivative of ln x. The derivative of ln x is going to be 1 over x, which is the caret, times the star feature, which is the derivative of x. So all of these blue boxes match back to the blue boxes that we looked at earlier in the notes. From here, I simplify my right side. I move down to the next step, and I bring over a y. From here, I distribute my y. Now, if we notice in pink, it says anytime you have a y, which I have a y right here, I have to replace it back with the original definition of y. This is what y is. So this should be x to the x, ln x. We learned earlier too, put a little or here, that if I have the same base being multiplied together, I can add my powers. So I could get this as a secondary answer. The last page is pretty easy. The definition of the derivative of a to the u has 3 parts to it. Repeat back exactly what a to the u is, times ln a times u prime. So notice, here are our trapezoids. To explain what this is, you may need to simplify beyond the initial trapezoid. However, there's the 3 parts: single line, double line, triple line. Single line, double line, triple line. If you have questions about this, again, use the homework helper.